Now we've arrived at the last lesson of this course on paradigms of computer programming. Recall, from the first lesson, we defined a paradigm as an approach to programming a computer based on a coherent set of principles or a mathematical theory. And we said that different theories of computing result in different paradigms. And in fact, each theory has its own way of looking at programming, highlights a different way of programming. But no one theory says everything. In fact, programming goes beyond traditional mathematical theories. It's a new discipline of which each theory only highlights a part. So in fact, we're still exploring how far programming can go, and I'll talk about that at the end of this lesson again. So in this course, we have covered 5 important paradigms. So the question that we raised in the beginning comes again. Why do we need more than one paradigm? Well, in fact, because each paradigm is a toolbox for solving certain kinds of problems. And when you want to write a big program, you have many problems to solve, so you need naturally more than one paradigm. And of course, using the right tools makes solving the problem much easier. Okay? So we saw 5 paradigms in this course, and we started by the first paradigm, which is functional programming. We talked about this in lessons 1 through 5. In fact, a substantial part of the beginning of the course was devoted to functional programming. So why is this? Well, it's not just because functional programming is an important paradigm. It's also because functional programming is a base, is a foundation for the other paradigms, and the technique of higher order programming in particular pervades all the other paradigms and gives them a lot of power. So functional programming is very important, and it's mostly because of higher order programming. We then extended this functional programming paradigm in 2 ways. The first extension was by adding multiple assignment, which we called explicit state, which is with a concept called cells. And this led us to object-oriented programming, data abstraction, different techniques based around data abstraction. And this we gave in lessons 7 through 9. And lesson 6 was devoted to semantics. So that was one extension of functional programming. We also did another extension where we added concurrency, threads, so multiple independent activities to the functional programming paradigm. Together with single assignment, this gives us a paradigm called deterministic data flow. We devoted lessons 10 and 11 to deterministic data flow. This is a very nice paradigm for concurrent programming. It's essentially a kind of generalization of functional programming, so all the techniques of functional programming remain useful in deterministic data flow, in particular no race conditions. We then, in the bonus lesson given by Seif Faridi, lesson 12, we then added another concept to deterministic data flow, which we called ports, which are named streams. In fact, this lets you add non-determinism exactly where you need it and nowhere else, because deterministic data flow does not allow you to express programs that need non-determinism, and sometimes you need it, like in client-server and other kinds of applications. But you don't need it very often. You need it in certain parts. So the best way is to have deterministic data flow as the default and to add the non-determinism where you need it. So we saw this in the bonus lesson 12. And finally, at the end of the bonus lesson, we combined multi-agent data flow and object-oriented programming to give a paradigm which I call active objects. So here we have agents talking to each other, message passing, but each agent is defined with all the power of object-oriented programming and living in a world where you have multi-agent data flow. So this is a very nice way of programming, combining the advantages of object-oriented programming and multi-agent data flow. So let's take a look at some of the kernel languages we saw. Each paradigm has its kernel language. We saw here, so this definition should now be familiar to you. This is the definition of the functional paradigm. So this is the base. This gives you all the basic programming concepts that you need for writing programs. So it has the basic instructions that you need, if, procedure, case. It has the basic data types, numbers, records. Notice that procedures are values, very important for higher order programming. Then we extended this to object-oriented programming. So how did we extend it? Well, we added state. So cells. In fact, we also add exceptions to this because it's an important part of object-oriented programming to use exceptions. So with these two additions, we can encode or define all the concepts of data abstraction and object-oriented programming. So notice we start with the functional paradigm and we've extended it. So that's object-oriented programming. Another extension going the other way is again starting with the functional paradigm, but now we add threads. Okay? So we start with functional here. We have this thread extension, and this lets us write deterministic data flow programs. So this is a third kernel language for the third paradigm. And now we have a fourth kernel language of multi-agent data flow. So we keep the thread extension. We then add ports. Ports which are named streams, which are a kind of communication channel. So semantically, ports and cells are equivalent. You can encode one in terms of the other, but it's interesting because for programmers, the expressiveness is different between ports and cells. So it's interesting to include ports specifically in the kernel language. And finally, we have our fifth paradigm, active objects. Active objects which combine the abilities of object-oriented programming with multi-agent data flow. So the behavior of each active object is determined by a class, and active objects communicate by message passing. We have both paradigms, both ways of thinking are useful, are possible in this paradigm of active objects. And the kernel language of this paradigm is the union of the kernel language of the two component paradigms. And I leave that as an exercise for you to write it down.